Welcome to the deep dive.
Glad to be here.
Today we're diving into the history of statistics.
Sounds like fun.
Yeah, we've got this Spanish book all about it.
Oh, fascinating. I'm looking forward to this.
Me too. I've always found statistics fascinating.
Yeah, it's a powerful tool for understanding the world.
It is. So this book goes way back, even before the 20th century, to guys like, Gauss and Laplace.
Right, those are some of the big names in the early days.
What were they working on back then?
Well, they were trying to grapple with variability. Data can be messy.
Oh, yeah, definitely.
And Gauss, for instance, he came up with the normal distribution.
The bell curve.
Exactly, the bell curve. You see it everywhere.
It's true. Heights, test scores, so many things.
It's really amazing. And Gauss also developed the method of least squares.
Okay, refresh my memory on that one.
So imagine you have a bunch of data points all scattered around.
Yeah, like a cloud of dots.
Right. And you want to draw a line through them, the best fit line.
Yeah, makes sense.
That's what the method of least squares does. It finds that line, even if the points are all over the place.
So it's like finding the trend amidst all the chaos.
Yeah, exactly.
Pretty impressive for back then.
Oh, absolutely. And then there's Laplace. He gave us the central limit theorem.
Okay, that one always sounded intimidating to me.
It's actually a pretty cool idea. Basically, it says that even if your individual data points are random, the average of those points will start to look like a bell curve if you have enough of them.
So even randomness has its patterns.
Right. And this was huge. These tools, initially for astronomy, started to spread to other fields.
I can see how that would be useful. Suddenly you can analyze all sorts of things.
Exactly. And the book talks about this guy, Quetelet. He was applying these ideas to society.
Quetelet, wasn't he the social physics guy?
That's him.
Yeah.
He was trying to apply the laws of probability to human behavior.
That sounds ambitious.
It was. He even thought traits like height and intelligence followed the normal distribution.
So he was trying to quantify human nature.
In a way, yeah. But you can see where that might get tricky.
Oh yeah, definitely. Not everyone fits neatly into a bell curve.
And that's one of the criticisms of his work. It can lead to some problematic assumptions.
It's a reminder that statistics, like any tool, can be misused.
Absolutely. And that's important to keep in mind.
Definitely. Yeah. So moving on from Quetelet, the book mentions Sir Francis Galton.
Ah, Galton. He was obsessed with measuring human traits.
Didn't he come up with the whole nature versus nurture debate?
He did, and he was definitely on the nature side.
He was big on heredity, right?
Absolutely. He studied family trees, trying to track how traits were passed down.
Makes sense. And that led him to the concept of regression to the mean.
Exactly. It's the idea that extreme values tend to be followed by values that are closer to the average.
Like if you have really tall parents, your kids might be tall too, but not as tall.
Right. There's a kind of pullback towards the average.
A statistical course correction.
That's a good way to put it. And this idea, it had a huge impact on the next big figure in our story, Karl Pearson.
Pearson. The book calls him a titan of statistics.
He was a major force. He founded the biometric school, which was all about applying rigorous statistical methods to biology.
Sounds like he was really trying to elevate statistics as a science.
He was. And he was incredibly influential. He even created the journal Biometrica, which is still a leading journal today.
Wow. So what kind of statistical tools did he develop?
Well, one of his big contributions was the chi-squared test.
Okay, remind me what that one's for.
So it's basically a way to see how well your data matches up with what you'd expect based on some theory.
Like if you flip a coin 100 times, you'd expect roughly 50 heads and 50 tails.
Right. And the chi-squared test can tell you how likely it is that any deviations from that expected outcome are due to chance.
So it helps you figure out if your assumptions are reasonable.
Exactly. But here's a funny thing. Pearson actually rejected Galton's work at first.
Really?
He didn't think math could be applied to fields like biology. He thought it was too messy and unpredictable.
So what changed his mind?
Galton's concept of correlation. Pearson realized that this idea that two variables could move together in a predictable way had huge potential.
Ah, so he saw the power of correlation.
He did, and he went all in. He developed sophisticated methods for measuring correlation and even declared that the science of the future will be biometrics.
Quite a turnaround. So he became Galton's biggest fan.
In a way, yeah. He took Galton's ideas, refined them, and really helped to establish statistics as a powerful tool for understanding the world. But there's a catch.
Oh, what's the catch?
Well, both Pearson and Galton were supporters of eugenics.
Ah, right. That's a dark chapter in the history of science.
It is. And it's a reminder that even brilliant minds can be influenced by harmful ideologies.
Definitely a cautionary tale. It seems like the history of statistics is full of both breakthroughs and missteps.
Absolutely. And that's what makes it so fascinating to study.
It does. So who's next on our statistical timeline?
Well, next up, we have Ronald Aylmer Fisher, who completely revolutionized the field.
Oh, I've heard his name before. He was a big deal, right?
A huge deal. He changed how we think about data and how we draw conclusions from it. But we'll have to save that for the next part of our deep dive.
Okay, so this Ronald Aylmer Fisher, the book calls him a statistical genius. What made him so special?
Well, he kind of shook things up, you know?
Yeah, how so?
While everyone else was focused on huge data sets, Fisher showed you could learn a lot from smaller, more carefully planned samples.
Oh, so it wasn't just about the quantity of data, but the quality.
Precisely. He brought this new level of rigor to statistics, and one of his big ideas was the statistical model.
Okay, I've heard that term before, but I'm not sure I totally get it.
It's like a mathematical way of representing how you think the data was generated.
So like a blueprint for understanding the data.
Yeah, that's a good way to put it. And Fisher said we need to be really careful about choosing these models. Then we can use them to make inferences about the population we're studying.
So it's like we're creating a map of the territory and then using that map to guide our exploration.
Exactly. And Fisher outlined 3 big problems in statistical inference: specification, estimation, and distribution.
Okay, break those down for me.
So specification is about picking the right model, like choosing the right map. Estimation is about using the data to find the specific values in that model, like figuring out where you are in the map.
Makes sense.
And then distribution is about understanding how much our estimates might vary because, our map might not be perfectly accurate.
Right, there's always some uncertainty.
Exactly. And Fisher had strong opinions about how to do all this properly, especially when it came to estimation.
What did you focus on there?
Well, he had these criteria for evaluating estimators: consistency, efficiency, and sufficiency.
Okay, those sound kind of technical. Can you explain them in plain English?
Sure. So consistency means that as you get more data, your estimator gets closer and closer to the true value.
So it's like zeroing in on the target.
Exactly. Efficiency means that your estimator makes the best use of the data you have. It squeezes out as much information as possible.
Okay, makes sense.
And sufficiency means that your estimator captures all the relevant information about the parameter you're trying to estimate.
So it's like you're not wasting any information.
Right. But here's where things get interesting. Fisher really didn't like Pearson's method of moments, which was the popular method at the time.
Really? Why not?
He thought it was inefficient. He even called it that traditional but inefficient method in one of his papers.
Ouch. Sounds like there was some tension there.
There was. They were both brilliant, but they definitely had their disagreements.
Well, I guess even geniuses can clash, so what did Fisher propose instead?
He developed the maximum likelihood method. It's a powerful alternative that's still widely used today.
Okay, maximum likelihood.
Yeah.
I've heard of it, but how does it actually work?
Imagine you're trying to find a lost dog in a park.
Okay.
You'd probably start searching in the areas where it's most likely to be, right?
Yeah, that makes sense.
Well, maximum likelihood is kind of like that. It helps us find the most likely explanation for our data, the values that make the observed data the most probable.
So it's like you're working backwards from the data to figure out what happened.
Exactly. And Fisher showed that this method often gives you more accurate and efficient estimates, especially when you don't have a ton of data.
Sounds like he was really pushing the field forward.
He was. And he wanted to share these tools with other scientists. So he wrote this book called Statistical Methods for Research Workers.
Was that just for statisticians, or does it for a wider audience?
It was for researchers in all sorts of fields.
Yeah.
He wanted to show them how to analyze their data properly,
Yeah.
to really understand populations and variability and draw solid conclusions from their experiments.
So he was bridging the gap between theory and practice.
Exactly. And one of the tools he helped popularize was ANOVA.
ANOVA, analysis of variance. I've always been a little intimidated by that one.
It's not as scary as it sounds. Let's say you're testing different fertilizers to see which one helps plants grow the tallest.
Okay, I'm following.
A two-test could tell you if there's any difference between the fertilizers, but ANOVA goes further and tells you which fertilizers are different from each other.
So it's more specific.
Exactly. It's like you're getting a more detailed picture of what's going on.
That makes sense. I can see how that would be really helpful for designing experiments.
It was a game changer. Fisher said, nature responds better to a well-planned questionnaire than isolated questions, and ANOVA was part of that questionnaire.
So it's about asking the right questions and getting more nuanced answers.
Exactly. And Fisher's innovations didn't stop there. He even applied his statistical skills to one of the biggest debates in biology: Darwin's theory of natural selection versus Mendel's laws of inheritance.
Wait, weren't those two theories considered to be at odds with each other?
They were, at least at first. Darwin's theory was about gradual changes over time, while Mendel's work showed how traits could be passed down in discrete units, these things called genes.
So how did Fisher reconcile those seemingly contradictory ideas?
With statistics, of course. He created these mathematical models showing how Mendelian inheritance could actually lead to the gradual evolutionary changes that Darwin described.
So they weren't actually incompatible, they were just different pieces of the same puzzle.
Exactly. Fisher showed that Darwin and Mendel weren't rivals, but allies in understanding evolution.
That's pretty amazing. He's revolutionizing statistical thinking, changing how we design experiments, and then unifying two of the biggest ideas in biology.
He was a remarkable figure. And to give you an idea of how innovative he was, the book talks about this analogy he drew between population genetics and the statistical mechanics of gases.
Gases. What do gases have to do with genetics?
Well, Fisher realized that both fields deal with huge numbers of individual things behaving randomly. Just like molecules in a gas, genes are constantly being shuffled around in a population.
So even though individual genes might seem random, when you zoom out to the population level, you start to see patterns.
Exactly. And Fisher was really interested in beneficial mutations, those rare changes that give an organism an advantage. He actually calculated the probability of these mutations surviving and spreading through a population.
So he was applying statistics to the very process of evolution.
He was, and his work had a huge impact on our understanding of how natural selection works. But, as impressive as all this is, we do have to acknowledge the more complicated side of his legacy.
You mean his views on eugenics?
Yes, unfortunately. That's a dark spot on his otherwise brilliant career, and we can't ignore it.
All right, so we left off talking about Fisher and his involvement with eugenics. Tough stuff.
Yeah, it's a reminder that even brilliant scientists can have some, well, pretty flawed ideas.
It's a complicated legacy for sure. So where do we go from there?
Well, the book also delves into Fisher's later work on the philosophy of statistics. He had some strong opinions, let me tell you.
Oh, I bet. What kind of opinions?
Well, he was a big critic of Bayesian methods.
Bayesian methods. Those are the ones that use prior beliefs, right?
Yeah, exactly. Fisher hated that. He thought inference should be based purely on the data. No subjective opinions allowed.
So he was a hardcore frequentist.
Through and through. He even rejected Bayes' theorem, which is like the foundation of Bayesian statistics.
Wow. So for him, it was all about objective data, no personal biases.
Exactly. But, Bayesian methods are becoming more popular these days, especially in fields like machine learning.
Yeah, I've noticed that. What would Fisher say about that?
I'm not sure he'd be too happy about it. But, Bayesian methods have their place. They can be really useful when you have limited data and need to incorporate some prior knowledge.
So the debate goes on.
It does. And speaking of debates, the book introduces another important duo, Neyman and Pearson.
Okay, what were they all about?
Well, they had a different approach to hypothesis testing than Fisher. They were less interested in just testing hypotheses and more focused on making decisions.
Ah, so it's about applying statistics to real-world problems.
Right. And they really formalized this idea of errors in decision-making. Like type I and type 2 errors.
Can you remind me what those are again?
Sure. So a type I error is like a false positive. You think something's true when it's actually not.
Okay.
And a type 2 error is a false negative. You miss something that's actually there.
Makes sense.
Yeah.
And those errors can obviously have big consequences depending on the situation.
Absolutely. And Neyman and Pearson said, we need to think carefully about these errors when we're making decisions based on data. Their work had a huge impact on things like medical research and quality control.
So they brought a more practical decision-making focus to statistics.
They did. But of course they clashed with Fisher, too.
Oh, no surprise there. It seems like everyone in the history of statistics was arguing with each other.
Pretty much. They had some fundamental disagreements about how statistical inference should work.
So even within this one field, there were all these different schools of thought, different approaches, different philosophies.
Exactly. And it's still like that today. We've learned a lot since the early days, but there's still plenty of debate and discussion.
Well, I think that's what makes it so interesting. Statistics isn't just about crunching numbers. It's about thinking critically about data, about how we use it to understand the world and make decisions.
Couldn't have said it better myself.
It's been quite a journey through this Spanish book, learning about all these figures and their ideas.
Yeah, it's been fascinating to see how statistics evolved from those early attempts to find order in chaos to the powerful tools we have today.
And it makes you appreciate all the work that went into developing these methods. Next time I see a statistic, I'm going to think about all the history behind it, all the debates and the breakthroughs.
Me too. It really makes you think about how we use data and what it all means.
Absolutely. Well, on that note, I think we'll wrap up our deep dive into the history of statistics. Until next time, keep exploring and keep asking questions.